So welcome everybody to the lecture number 12 or so of the semester. And when you recall what we did last week, we essentially did basic number theory, some mathematical preliminaries. In particular, Euclidean algorithm, extended Euclidean algorithm, and that was the math part. So that was the theoretical background for the fun part, and the fun part comes today. We're going to talk about RSA, which are these three young guys over there. They're not young anymore, okay, but they're in their 50s or so. They're great people, and they invented the most famous, most widely used public key crypto system. So we're going to do that, and it's a super important lecture because this is essentially what's in your web browser. Okay, it's used all over the world, in particular in the internet. Very, 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 very super important crypto system. Okay. We're going to do three things. We start with an introduction to PK. Whenever you see PK, it means public key, or asymmetric cryptography, public key. The two main parts of the lecture, just to warn you, okay, so kind of the middle part of the lecture, you have to be awake, which is talking about the RSA crypto system itself, the algorithm. And then this part is about fast exponentiation, which is an algorithm for implementing RSA. Again, be awake, okay? It's about 60 minutes in the middle of the lecture. Towards the end, you can go back to sleep. We're going to talk about the security of RSA. Very important stuff is going to be on the exam, okay? Pay attention, be alert. Okay. So we start with chapter number 1, Introduction to Public Key Crypto and also very brief introduction to RSA. So what we want to do, what I want to do first, we want to look at the stuff we did so far. That means our current view on cryptography is symmetric cryptography. So if you have symmetric algorithms, we want to use them, and right now we only focus on encryption of data. There are all kind of other things you can do with cryptography. Right now we're just doing encryption of data. So we have this picture, which you've seen many, many times, and it's getting boring. You have Alice and Bob who want to communicate with each other over the unsecured channel. You know, that's the bad internet. Can we be quiet? Hallo? 7. Reihe da. Ruhe. Sie können schlafen. You can go to sleep right now. Just don't talk, okay? I'll tell you when you have to wake up, and don't talk until then. So we have this setup, and we've seen that again. We've seen that dozens of times in this lecture. We do an encryption here, and we do a decryption here, and that works fairly well. However, it requires that Alice and Bob share a key. And what is symmetric about the setup? Why is that called symmetric cryptography here? What is symmetric about it? Yeah. The same key, right. And you can, that's the symmetry axis, right? Symmetrieachse, achsensymmetrisch, right? And, left and right is the same key. It's not very complicated. And what is the big practical problem we have before we have the situation? What do you have to do before we get the setup? Yeah, distribution of keys. We have to get the keys over, right? So what we need is a secure channel, which is a pain, right? This is painful, right? It's schmerzhaft. This is cost, and in particular, it doesn't work very nice on the internet, right? If you have large networks, the secure channel situation is not pretty, okay? So, and an analogy, which is not very deep, and I just want to show you a picture from the book. an analogy for this type of system is, one moment, I just go, we're almost there, is in our textbook, and it's, most books have that, and I think it's somewhat useful. So one way of viewing symmetric cryptography is saying we have a safe, and putting something in the safe, you know, one of these Leitsordner, right, one of these German file sorting things, is putting it in the safe. And now Alice, if Alice wants to encrypt, she takes her key, opens the safes, puts something in, locks the safe, right? This is encryption. For decryption, Bob also has the key, the same key, by the way, right? So Bob takes his keys, goes here to the safe, opens the keys, and can decrypt, meaning he can extract the piece of papers, right, the files. So this is a very simple analogy, and this is roughly what's happening. And this was state of the art, you know, starting in ancient Egypt about 4,000 years ago until 1977, at least in the public domain. People thought this is the only way of doing cryptography. And now it's getting interesting. What asymmetric cryptography does, asymmetric algorithms, is based on the very basic operation is simple, and it's a little bit surprising, even though it's very simple, is we can switch to a different model. The very basic initial thought of the inventors was, do we really need a key for encrypting something? Because encrypting by itself is not that critical. The thing that is really critical is decryption, right? So now the model for public key cryptography is that, let's say, Bob has now two keys, okay? Bob has a private key, which is pretty much what the symmetric keys are about. You know, they keep them to yourself, that's the private key, but you also have a public key, okay? The idea of the public key, wir fangen 7:15 an, ja, und da ist auch eine Treppe. The idea of the public keys, and this is a revolutionary thing, that you create a key which you put on your website. So you make a key very, very public, and you put it in a phone book. That was the original analogy in the 1970s. So you have a phone book, and it doesn't contain your phone number, it contains your crypto key, so everybody can look that up. So clearly you can't use that for decryption. If somebody gets this key, the person can decrypt. But it's a public key, so it means that, which is, you know, in green with the green box here. So the idea is you use this public key, and I have my public key literally on my website. So you can go there, download the key, and put something in the box, something in the safe. That means this green key, the public key, is only used for the first part for encryption. So encryption happens from now on with the public key. And for decryption, this is similar to before, only a secret key should be used. And it's not called a secret key, it's called a private key. Okay, so this is a very basic thought. If we are able to do that, we can come up with a simple protocol. I want to draw another picture here. I want to do that a little bit more abstract, but only mildly so. So Bob, and this is a new concept, be awake, has two keys. Before, everybody had one key which happened to be the same key. Now, Bob has two keys. A public key, again, this is being put on the website, it's being put in a phone book, whatever, in a registry, and a private key. The public key is being sent to Alice, or often more realistically, Alice actively pulls it from the website, but it's not a secret piece of information. And in particular, you know, bad guy Oscar also has access to the public key. That's the interesting thing. Before, we need a secure channel. You know, as soon as Oscar gets hold of the key, he can decrypt, and, you know, he won and Alice and Bob lost. This time, this is the interesting thing. Oscar can read the public key, and it's of no use to them, hopefully. So what happens then, now if Alice wants to encrypt something, Alice uses the encryption function, she encrypts her message X, and file, email, hard disk, whatever, piece of music, using the public key, okay? So that's the green key, that's the green boxes in the drawing. Alice sends the ciphertext over it, as before, over the unsecured channel. Of course, Oscar can observe this, Oscar can observe that and read. And on the receiving side, for decryption, Oscar uses, of course, the ciphertext, and now, but he decrypts with the other part of the key, which has to be very secret, has to be kept secret. Okay, that's it. This is public key cryptography in 5 minutes. Okay, that's the basic idea. And now the big question, obviously, are what is E and what is D, right? What is the encryption and decryption function? And one very pretty solution to that is RSA, the RSA public key crypto system, which has become the most important public key crypto system. And that's what we're going to do today. Some facts about RSA, and it's just very, very simple. So that was invented in 1977 by Ron Rivest, Adi Shamir, and Leonard Edelman. And that's where the name stems from, RSA, okay? The invention was triggered indirectly by a paper from 1976 by Diffie-Hellman, and they are kind of the real inventors of public key cryptography together with Ralph Maracle. So they were triggered. Some of the ideas came from the paper by Diffie and Hellman, and we're going to talk about that either next week or after the break. But this is kind of the two very important papers that started the field of public key cryptography, and that's kind of the second one. The first paper was a year earlier, and we're going to talk about that again in the next few weeks. One fact which I mentioned a few times is the most popular public key, is an abbreviation again, most popular public key crypto system. The nice thing, and once we start about Diffie-Hellman, I'm going to talk more about this. The nice thing about public key cryptography, that means way of realizing this, this type of setup. There are only essentially three families of public key crypto system, which is great. Unlike symmetric key cryptography, we did DS here and we did AES here. In reality, there are a few hundreds of these, for instance, block ciphers, and there are probably 100 stream ciphers or so. There's a few hundred symmetric key algorithms. There's no way we can ever do them in a lecture. In the public key case, it's much easier. There's essentially three types of crypto system with practical relevance, I should say. So out in the wild, in the real world, there are only three types of algorithms being used. There's RSA, there's discrete logarithm system, whatever that is, and elliptic curve cryptography, and we're going to do all three together. Okay, this is number one is RSA, and then comes discrete logarithm. We need 2 or 3 weeks for that, and then come elliptic curve, and again we need another 1 or 2 weeks with that. And by the end, around end of May, you will know all public key crypto system that there is to know for use in practice. There are a whole bunch of other more exotic public key crypto system, but in practicality there are only 3. And again, we're going to do the first one today. It's very important. I don't have hard numbers, but my guess it's the market share, counted by the number of implementations that are being used. Again, there are only 3. RSA is the biggest one. I don't have numbers. My guess is maybe 70%. Maybe 70% of implementation or 80% use RSA, and then there's another 20 or 30% is being used by the discrete logarithm system. Maybe I'm off here, but that is my guess, okay? RSA had a little bit of problems being really widely used because it used to be patented, but only in the USA, but it expired a while ago until the year 2000. This is just a little bit of a real world fact. Okay, so this was the warm up. Now we come, and we're done with the first part of the lecture. The first 20 minutes weren't that bad, right? It's essentially this here, and again, looking at this block diagram, it's a simple protocol. Now we want to come up with function E and D that encrypts with a public key and decrypts with a private key. Okay, and of course the challenge is, maybe a little bit jumping ahead, we want to encrypt using a public key which is known by Oscar, yet Oscar cannot be able to do this decryption. This is of course the hard part, right? Doing some data scrambling, everybody can do that using a key, but now Bob must be able with the right key to decrypt, and Oscar is not able to do that. That's the hard part. So we start the second chapter, which I call the RSA algorithm. Okay, and we have two subchapters, two sections. One is called 2.1, where we talk about the key generation. And I just want to write this a sentence down. Unlike symmetric algorithms, and in parentheses AES, triple DES, or whatever, comma, public key algorithms require the computation of the pair K public, comma, K private. Okay. The interesting thing here is, obviously, we need a K public, K private. There's maybe somewhat of maybe the most important word in the sentence is computation. They have to be computed. Unlike AES or DES, probably you don't want to compute the secret key. You want to have something, a true random number generator. Here is math involved, and pretty hefty math that you will see. That's why we have this, subsection key generation. In RSA, it's doable, but to give you an idea, for instance, to come up with these keys or the parameters, for instance, with elliptic curves, it's sometimes you need a few hours of computation to generate good elliptic curves. Okay, it's not as bad in RSA, but this is essentially a step that is missing in symmetric ciphers. If you do AES, there is not really a complicated, involved scheme to compute keys. Okay, so now we do that, I think, on the next board. We need a little bit of space. Now, just give you the a 5-step approach to computing the parameters. The first thing what you do is, so this is now key generation, okay? Choose large primes, and they're almost always called P and Q in the literature. I guess P for prime and then Q because it's the next letter in the alphabet. Okay, it's not very. You could have probably called it P1, P2, but they're always called P and Q. This next step is you take the 2 primes and you multiply them. This is not very complicated. And the product, again, is almost always in the literature called n, okay, which is maybe the most important parameter in RSA. Okay, that's the and it ends up being the modulus. Now we need something which was very strange until 7 days ago, which is the Euler's phi function, phi of n. I talked a little bit about that. And it turned out it's really easy to compute phi of n. Under which condition? What do we have to know about n in order to compute that quickly? Yeah, we need it. Yeah, with the product of prime, exactly, product of prime, we need the fancy way of putting that is saying we need the prime factorization. If you have an integer, if you know the primes, you know that out of which the integer is composed, it's really easy to do, and there was this uppercase pi, and das große Pi symbol, dieses Produktsymbol, and it turns out for this special case of product of 2 primes, it's p minus 1 times q minus 1. You remember there was one homework problem for that, right? Now this is why we did it. Okay, it's really useful. Okay, so this was all warm up, right? It was part of the warm up phase. Now we really talk about generating the keys. Right now we haven't generated any keys. The first key is the public key. This is almost always in the literature denoted by a lowercase e, kleines e, okay? E for encryption. Why E for encryption? Because at this point, the public key actually does the encryption. That's why you use an E here. And surprise, surprise, the private key will be called D for decryption, okay? So. Oops, wrong board. Okay. Again, you can choose it, and it's also, this is very different from symmetric key cryptography. In symmetric key cryptography, all keys must be random. Essentially, you have to do, you have to use an euro coin and, do coin tossing, right, to generate 128 random bits. This is just choosing. It doesn't say choose randomly, choose. It doesn't have to be particularly secret, okay? It doesn't have to be secret at all. It has to come from a certain set, of course, namely from the set 1, 2 up to phi of n minus 1. And remember, phi of n, computing phi of n is not very difficult. S dot T dot bedeutet means such that, so das. That means with the following additional condition, the GCD of E and phi of n must be 1. Okay? Another way of putting that is saying E, that means the public key, and phi of n are relatively prime. Okay? We talked about this condition a couple of times in this course already. Does anyone know if this condition is fulfilled, which value exists then? Do you know? The inverse, exactly. So the inverse, and you see E is smaller as of this, so it's probably the inverse of E. And it turns out the inverse of E is the private key. That's it. Okay, computing inverses is something very, very important. You have some essential, a freely chosen parameter. If you compute the inverse, that's the private key. Okay. So now we have to do that. So we compute K private, and we call that D. I mentioned that before. Comma, such that, so dass, the condition is D times E must be equal to 1. And now I just warn you, because this is a beautiful thing to make mistakes here. modulo phi of n. Okay, and I'll tell you in a second why this is easy to make mistakes. So for the key generation, we do arithmetic modulo phi of n. That means the two keys are the inverses of each other modulo phi of n. You say, why is it easy to make mistakes? Because you will see in 5 minutes, actually doing encryption and decryption, doing actually RSA is always modulo n. Okay? Normally, kind of your brain will get used to, if I see RSA, I compute modulo n, except in the key generation phase, which you only do in the beginning of RSA, there's at one point you have to compute stuff modulo phi of n, okay, just to warn you. So that's it. There are 5 steps here. And I guess we put that in can put a frame around that, box that in. This is very, very important. And it seems, they seem quite random, right? Quite arbitrary, zufällig, willkürlich gewählt. This set of 5 steps is going to be very important. If you finish studying here, this will come up over and over and over again. They're super important steps in modern cryptography, okay? And if you do enough example, at some points they will become part of your general knowledge or whatever, Weltbild, right? So now at the end of the step, the main thing we get out here is the public key, and it was a little bit, pub E is only part of it, and probably the main part of the public key, but strictly speaking, the public key has 2 parts, namely this value E, but also this product N here, okay? What you get also out is 1 parameter for the private key, which is this value D. Okay, so I just want to put a few remarks down here right next to the box here. So if you have space in your notebook, write it on the right hand side. So here I said choose large primes, and large is kind of a very soft adjective, right? What do we mean large? Well, we mean really, really large. Namely, in practice, P and Q nowadays should have at least 512 bits. Very, very often you want to get twice the length. That means P and Q, each of them are 1024 bits, about 300 decimal digits. That means if P and Q have 512 bits, does anyone know how big the product is, N here? This has 512 bits, this has 512 bits. Anyone know? Anyone good? Yeah? Yeah, exactly. You add them up, 1024 bits. So this becomes, okay. And again, today, for reasons that if we have time, we discuss towards the end of the class, you need twice that, okay? You need 2048 bits. Things get long and slow if you implement it in software. Phi of n is easy, this is easy, and maybe the last remark here. So here you just choose something. This is multiplication. We don't have to talk about that. How do we compute the inverse? What is our favorite algorithm? Yeah, very good. Extended Euclidean algorithm. Okay. See last week, compare last week, okay? Compare homeworks that you did last night or this morning, right? This is why we did that, why we force you to do that, okay? Okay. So this is, the first step is 2.1 key generation, and yeah. Yeah. It's good. Very often in practice, let's say with PGP, you can choose the key length. They say, use RSA 1024. A very good question. Is that this 1024 here or here? It's here. You always talk about N. This N kind of gives you the security parameter. The longer, the more secure. So it's not very complicated, this thing. If people say we want to have RSA with at least 1024 bits, they mean n 1024 bits, you divide that number by 2, you get the length of the 2 primes here. Okay. Good. So now we're done with the key setup. So we haven't done any actual encryption, right? So if in this very simplistic block diagram, we're done with this step here, right? Okay. In particular, what we have not done is we haven't addressed the question marks, the Fragezeichen here, right? How do we do encryption? How do we do decryption? And this is going to be the next section, which actually fits in here. (2.2) is RSA encryption and decryption. The nice thing about RSA is this is kind of a little bit involved and very arbitrary looking. Now the beauty of RSA is conceptually this is super easy. This is one very simple, very simple operation that does encryption, and then another very simple, another very simple operation that has decryption. It's very simple, okay? So encryption works as follows. Given, what is given? The public key consisting of n, which is called the modulus, and you will in 60 seconds you will know why n is called the modulus, given K public consisting of n and e, and a message, we encrypt a message, and the message now has restriction. It must come from a certain set, namely from in Zn or Zn, consisting of the numbers 0 up to n minus 1. Okay. And now the actual encryption computes the ciphertext y. This is our standard notation we used for, since the beginning of this course. And now comes, be awake, now comes the big RSA formula, which is laughably easy. You simply do an exponentiation. That's the whole encryption. You do an exponentiation, c'est ça. Okay, we're done. And everything modulo n. This is red frame number 2, roter Kasten Nummer 2 for today. And there's much to say about that here, at least for now. There will be much more to say, but for now there isn't much. At least conceptually it's pretty easy, right? You take x, you take e, which we computed here, somewhere, here. And you take it modulo n, which we computed here. So once you're done with this, which is a little painful to do that, the actual encryption seems pretty easy. So this is what Alice does in our example. The right-hand side does the encryption. You send stuff, the left-hand side, sorry. And this is your right-hand side. Now you decrypt, so Bob, upon receiving the message, Bob has to decrypt. That means Bob, given y, Bob would like to recover x. What do we do? It's very similar to before. What's given now is K private, which is this parameter d, and y, which is the ciphertext, which is, of course, if you do modulo n operation, you get a result in the range 0, 1, 2, 3 up to n minus 1. So y is again in this ring Zn. And what we do, x is the decrypted version of y using the private key. Again, our standard notation holds. And this is equivalent to y And again, you do an exponentiation just with a different exponent, namely the private key. Y raised to the dth power mod n, and that's it again. Okay. So this was a lot of formula, many more formulas than we're used to without, major motivation. I would like to do at this point, I would like to give you an example, which we... Yeah? Yeah, so he summarized, chapter number 4 we want to do today. RSA security is excellent. He's much too smart. You can go home now, so for the rest of the day. So he said the whole security relies on, beruht auf, hängt dran, hinges on, the fact that, I can tell you that now at this point. So Oscar would like to do the same, right, obviously. Oscar sees Y, the ciphertext he would like to decrypt, so what do you have to do? What is the one information Oscar does not have? Which is the one parameter he would like to have? Yeah, which is D, right? He doesn't know D. How do we compute D? Well, D is here, extended Euclidean algorithm, right? He watches the video, he buys my book, he knows how to do that, right? He goes to Wikipedia, right? It's cheaper, so he goes to Wikipedia. He knows how to do that. But what is the problem? Why can he not compute D? Why? He is Oscar. What is the problem for Oscar? He knows the Euclidean algorithm. He was in my lecture. He knows E. What is the thing what's the problem for him? Yeah. Phi of n. Well, phi of n can be computed, right? There was this formula. It's really fast, Professor Parr said. Yeah, the formula is here, but the formula is only fast if you know P and Q. Okay. It turns out, if I give you a 1024-bit number, that's about 300 decimal digits, so 300 Dezimalstellen. If I give you a 300-digit number, you cannot factor that. Nobody in the world can factor that. It's very hard. The factoring record is 650 bits or so. We cannot do 1024. We definitely cannot do 2000 bits. Okay? So this is factoring. With factoring, it's easy for Oscar to attack the system. Once he's factored, he can compute phi of n. He knows E anyway, that's a public key. He knows phi of n and he computes that. This is why modern public key cryptography and factoring are really closely related. Excellent remark. I'm jumping ahead with this lecture, but that's fine. So now I want to do an example. Example for what? I want to rebuild this protocol here, right? So we have our friend Alice, we have our friend Bob. So now we do, this is cookbooks, this is boring, this is almost, not worth to do at a university, we do it anyway. We do cookbook, we do step 1, 2, 3, 4, 5 with small numbers, not with 1024-bit numbers. So Bob starts with step 1, choose P and Q, and we choose 2 very small numbers. P is 3, Q is 11. Okay, so we can do most of the arithmetic we can do by hand. Number 2 in our recipe book is compute the product and P times Q, which is 33. Step number 3 of the key generation protocol is computing phi of n, which is P minus 1 is the, can anybody do that mentally without supercomputer? It's 20, right? 3 minus 1 is 2, 11 minus 1 is 10, so it's 10 times 2 times 10, sorry, is 20. So we're done with step number 3. Step number 4 is choosing a public key, and I choose a small public key here. Okay. I choose e equals to 3, which is really bad as an example. I'll do it anyway, because this is equal to this one prime number. It's just there aren't that many small numbers. Okay. E doesn't have to be equal to p, right? This is a big coincidence. RSA works anyway. So I tried pretty hard to come up with a good example for RSA. It's not that easy. I would like to have an example where you can do everything by mental arithmetic, by Kopfrechnen, right? It works so la la. There's one point at, in 2 minutes where it's getting a little hard. Step number 5. Oh yeah, by the way, is this GCD condition fulfilled? Is E and phi of n, are they relatively prime? What's the GCD of 20 and 3? That's 1, right? It's fine. So that's part of the problem. You can try 4, but then 4 is not relatively prime, and 5 is not relatively prime. 6 is it's only 7, and then the numbers become big. So that's why I chose 3. Now we have to compute D. D is the inverse of 1, inverse of 3, which turns out to be actually 7. Modulo phi of n modulo 20. There's a little. Let's see whether we're doing the right thing here. D times E is 7 times 3. What is 7 times 3 modulo 20? It's 1. And that's the GCD condition, right? Where is that? Here. The example is fine. I'm not lying to you. Okay. So now we're done with the setup phase. Let's look in the protocol. What does the protocol tell us to do? Können wir da auf den billigen Plätzen da? Ja, Sie ruhig. We send the public key over at this point here. Okay, it's the first part of doing the actual crypto stuff. Let's do that. So we send over K public, which consists of the modulus n, which is the 33, and the public parameter e, which is 3. Okay? Now we're here in the protocol. Let's jump to the next step is we actually want to do encryption. So let's do LSD encryption. And what is the encryption function? What is the question mark? Well, the question mark got answered in form of this red box here. This is what Alice has to do. What I assumed a message X with the value 4. Okay, not very sophisticated. Now Alice encrypts. What does she do? Well, she takes a message 4, raises that to the eth power to this here. This is n, e. Raises this to the power e, right? Hoch e nehmen. And e is 3. Anybody really good? 4 times 4 times 4? Any? 64. Very good. 64. And now you have to reduce modulo, namely modulo, where's n? Modulo 33. Can anyone do that without calculator? 64 modulo 33. What is that, mod 33? This is 31. Very good. Okay. So now what? Going back to the protocol. Once we computed the ciphertext, it's a nice thing about the ciphertext. It's encrypted, so we can send that over the internet. Means we can put that on the channel. We send Y over. On the receiving side, Bob has to decrypt. And how does this work? Well, this was this framed box here, this framed formula. Again, takes the ciphertext, raise it to the private key's power. That means this is, hopefully, this is becoming X, right? X is computed as taking the ciphertext to the d's power, which is 31 to raise to the 7th. And this is this one point in time where it's hard to do mental arithmetic. I'm going to give you a point in a second how to do that anyway. This turns out to be 4. You know, this is my funny notation here. You know, this is an exclamation mark, Ausrufezeichen. Right? This is my invention, right? It's actually the invention of my math professor when I was in second semester. And why is that a great thing? Because this is the same thing we had at this point here. Okay, modulo, again, modulo n, and n was 33. Okay, so after decryption here, we develop that. So the one frustrating thing is that here you need a pocket calculator here, right? And now I'm going to show you a little cute trick related to modular arithmetic, which has nothing to do with RSA. And if you hate mental arithmetic, if you hate Kopfrechnen, you can sleep for 2 minutes, okay? If you like Kopfrechnen, modular arithmetic, you can be awake. I want to show you a quick way of doing that. Again, this has nothing to do with RSA. It's off topic, outside the lecture. You know, switch your laptop on, watch YouTube or whatever, right? That's fine. So I want to do, of course, you can do you can actually do, you know, arithmetic by hand and schoolbook multiplication. There's a very neat trick, namely, 31 is pretty close to 33, right? And what happens if you replace 31 by a negative number, modulo 33? Which one is that? Does anyone know? It's equal to -2, so this is you remember we did this equivalence class and stuff in, I think, the second lecture. You can do that. Mathematically, 31 is the same as -2 if you do mod 33 arithmetic. The nice thing is 2 is a much smaller number than 31, right? I think I asked you at some point, please memorize, auswendig lernen, memorize the powers of 2, right? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Just remember them. If you're lying awake at night, if you wake up too early, if you wake up in the night, go through your head the first 10 powers. It's really useful at this point in time because I'm doing that always when I wake up early. This is 128. Okay, so I can do this exponentiation pretty quickly. Mod 33. And now things become pretty easy. Because this is now four times 33 is 120. What? 132. What am I doing wrong here? I'm doing something wrong here. Das ist 132, aber dann kommt der es ist minus 4 times, this is minus 132, right? And what is the correction term I need at this point here? Are you anybody really good with Kopfrechnen here? It's 4. Okay. So now I'm going to take this mod 33, and this becomes 0, right? So, okay. That's it. Okay. I didn't need a pocket calculator. That's the thing. Back to RSA, so this was intermezzo here, right? Okay. This is just to show you even this seemingly complicated operation, if you're creative and you know your modular arithmetic rules, you can do in your head, right? Okay. So what is now missing with RSA is 2 remarks. Okay. One thing which is really important, I mean, we're not going to do due to time reasons here, is to prove that decryption and encryption are actually inverse operations. I show, in this case of the example, in the case of the example, it worked, which was a little strange. Maybe I should have mentioned that before. I take my x value, my message, raise it to the power, and I get some value, 31. I take that 31, I raise it to the different power, I get the original value out. There's a little strange thing that's happening here. It's not very intuitive. It's nicht sehr intuitiv, gefühlsmäßig. This is not what I expect. I do one exponentiation, I do a second exponentiation, and they cancel out. I get the original value again, right? So in order to show that this always works, if I do x to the e, and then I do the result raised to the d, if this condition holds, this is a condition on the exponents, right? D and e must be the inverses of each other mod phi of n. They must be inverses of each other mod phi of n. This is what's called the proof of correctness, and we're going to do that in the help session, in the Übung, right? But I just want to write that down. Proof of correctness, this is in the Übung, and if you can't wait till Monday, or page 178 in the textbook, as the first remark. Second is, we just saw an example. In the real world, and I mentioned that before, real world, RSA parameters are very large. Compare page 177 in the textbook, and I think, yeah, I'll show you that. I think I just wrote them down. We just put that in the book. I think it's kind of good to have, if you see them once in your lifetime, if you see how. So this is how RSA looks in practice. You get pretty long okay. This P, Q, N, E, and D is a real-world example. Jan, with whom I wrote the book, Jan Pelze, computed them. Okay? So this is the numbers you're dealing with. I didn't want to use them on the blackboard. You know why, right? So this is, okay, but this is just to get a feeling. Things are really, really long. Okay? Also, maybe one remark. There is, to my knowledge, there is no other, hello, who is that? There's no other technical applications, or there's no other technische Anwendung where you have to deal with such long numbers. If you have a fancy cell phone, this German professors have, right? There's all kind of multimedia stuff happening here. Data compression, you can watch videos. There's a lot of stuff happening there in terms of algorithms. There's the communication algorithms to establish the link, right? All kind of stuff. They're very complicated. All of that stuff is not easy to do that, right? None of all the algorithms, data compression, doing error correction stuff, needs arithmetic with such long numbers. So this is something that is unique to modern cryptography. Okay, this is just Allgemeinbildung, right? So this long number stuff never happens in any other applications. This is only public key crypto. Okay. Okay, so that was number 2 of today's lecture, and this was the first very super important part, is doing RSA. Now you know what RSA is, and you can get, you know how we operate, so you're going to get homework assignments, and you have to compute 500 of these examples by hand with a pocket calculator, right? So, it gets imprinted, eingeprägt in your brain, right? We really want you to hate these 3 red boxes, right? And a good way of hating is, just do that 50 times, right? I'm exaggerating, but this is a basic idea. I mentioned that, right? This is this Zen, right? Zen thing, Zen Buddhism. They say if you want to do things really well, you have to do them 30,000 times. 20 times is enough for us, but I think it's a good metaphor, right? The more you do things, the better you get, and even you hate Päckchenrechnen, right? That's why they do Päckchenrechnen in the Grundschule, right? Kleines einmal eins, right? You do that essentially 2 years, right? Our third kid is just in third grade. You do for 2 years, you just do Kleines einmal eins, it's because you become better and better, and it's really useful in life. It's a little bit with RSA, the more of the stupid examples you compute, the more of a feeling you get. So now comes, I think, for me personally as a teacher, and I'm in a different position than you are, I think that's the fun part of today is doing fast exponentiation, okay? Now, if you want to implement, and this has not to do with the algorithm, with the mathematics per se, or why the algorithm works, but if you look at these numbers, and they are in hexadecimal notation, it would almost be better to show them in binary with zeros and ones, and we actually would have 1024-bit long numbers, right? P and Q would be 500 bits, but N, D, and E would be 1024 bits. So what I want to talk about now is the practical side of RSA. And what I want to focus on is not so much this here, because this can be done this is actually what is hard in practical term is generating 2 large primes, and maybe we do that in the Übung, in the help session. But there's one thing which is very important. It's so important that I want to do that with you here, and I think it's really, really fun. I love that, the next topic. Namely, in practice, your web browser, every time you want to encrypt your credit card number, if you buy something at Amazon or eBay or whatever, you don't have to do that every time. Why? Because this is setup time. And normally you set up your RSA parameter once, and that's it, till the end of the lifetime of your smart card, for instance. If you have a smart card with RSA on board, this is being done literally in the factory when the smart card is manufactured, more or less. But you do that only once. D, E, and N are being burned on your Geldkarte. It's not on the Geldkarte, but whatever. And there are bank cards that have RSA. It's being put on the Geldkarte. That's it. That means we don't have to worry about the red box anymore. But now, every time you encrypt stuff on the internet, every time you establish a secure session to Amazon, you have to do this stuff. So what I'm trying to motivate here is it's pretty important that we do this reasonably well. So the question is now in the third chapter of today is, how do we do this fast? And they're both exponentiation. So now we want to talk about fast exponentiations. And now I want to look how to implement. Implementieren heißt bauen, yeah. Yeah, it's try and error, and it's even worse in practice. There are few E values that are very, very popular, in particular small E values, okay? And one value that is popular is 17. Yeah. And 17, yeah, it's pretty unlikely that that one of those, just in terms of likelihood, that one of those has P minus Q or Q minus 1 as 17 as a prime factor, and that this is fulfilled. Of course, you have to check that. But the other thing is you choose something random and you check here. It's not that hard to find one. In most cases, just you pick one and that's it. Okay, it's a good question, but it's not hard. It's not hard. Hard is finding P and Q, but again, this is not something I want to do today here. So what I want to do is fast exponentiation. That means implementing. If I want to implementieren heißt bauen, right? I want to build this here. How do I do that? And actually, I want to split that in two subtopics, subsection. I want to do an introduction, so general. Again, the motivation is that we have the following problem. In practice, we have to compute x to the e for encryption, and we have to compute y to the d, both mod n. This is encryption, this is decryption. You don't have to copy that, it's here, right? Just to make nice notes for your notebook. And exponentiation per se isn't that bad. We know how to do exponentiation. Unfortunately, we have to do exponentiation with those numbers, with really absurdly large numbers. So with very long numbers. And this is the topic of chapter number 3 of today. How do we do that quickly? Okay, and let's start with a few preliminaries, so some general thoughts. How do we do exponentiation? So we do an example. Where do we do that? That might work here. Let's start simple, x to the 4th. Okay, how do we compute that? So the naive way of computing that is computing x times x is x squared times x is x cubed, x hoch 3, and x cubed times x is x to the 4. Right, of course, right? Of course should be a reaction. What else should we do? And what are the costs here? Eins, zwei, drei, 3 multiplications, okay? So now, oh, by the way, wake up. This is next 10 minutes, very important. You don't want to learn that from the book, what I'm going to show you here, please, okay? The first question, this is a question you should take very serious. Are there any ways of doing that with less than 3 multiplications? And don't look in the book, because then it's easier. Yeah? Yeah? Exactly. So that's naive way, and I call that better way, okay? The better way does, of course, you have to, when you start with x, the only thing you can do is compute x times x. I guess you can compute a square root or something crazy, but this is the only reasonable way. And now, your kommilitone just said exactly the right thing. Why multiplying with x? Why don't we take this x squared, this larger value, and multiply that by itself? And this gives us 2 multiplications. Great, right? You say this is really, it's not, right? It doesn't seem barely worth it. But in practice, we're not doing x to the 4th. We do x to the, really bad, right? Really long numbers. So let's look at another example. We want to compute x to the 8th. Again, we start with the naive way, which is a very polite way of saying the stupid way, right? We just do this very stupid thing. We can only multiply by x. So you do x by x is x squared. X squared times x is x cubed, x hoch 3. And at the end, you do x to the 7th times x is x to the 8. And this is 1, 2, 3, 4, 5, 6, 7 multiplication. And then we had this really cool trick here, right? Instead of multiplying by x again, we multiply by x squared. Let's see how that works in this case. We do x times x is x squared. X times x is x to the 4th. What should we do next? Yeah? Exactly. Multiply x to the power of 4 by itself, x to the 8. Why am I doing that? Because maybe here we saved one multiplication. Here it's getting a little bit more interesting. We reduce, we save more than 50% of the workload, okay? Now in practice, 8 is not a particularly impressively large number, right? These are 4 bits. Again, we have 1024 in practice, right? So just to give you a feeling, so how do we deal with this number? How do we deal with, okay? Again, the naive way, this homework assignment, okay, so. How many multiplications? Whoever says 1024, I'm going to kick out of this university, right? It's not 1024, but, yeah. So this is 2 to the 1024. And if we exact, right, it's always -1 here, right? The problem is, even if I had a lot of time, means more time, the end of the universe, I would run out of chalk, out of Kreide, right? I asked it, right? I think there are about 2 to the 200 or 2 to the 300 atome in the known universe. So there are not enough atoms for Kreide, right? I cannot write that down, even if I get really, really old, right? And the sun cools down everything. This will never, ever, ever, ever work, okay? 2 to the 1024 is a really bad number. So how far are we? And this is too unfortunate, right? Can I squeeze it in? So please write that down on the left-hand side. The better way of doing is starts with x times x is x squared. X squared times x squared is x to the 4th, blah, 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 blah. It would take me 2 hours, probably, or 3 hours. I could do it. And there's enough chalk in this box to do that, right? I don't need 2 to the 300 atoms for doing that. That's what I'm trying to say. At the very end of my letter here, I end up with x to the 1023 times x2 to the 1023, which gives me x to the 2 to the 1024. Everybody with me? How many steps do I have here? Can anyone see that? You just look at the exponent, right? This is to the 0, to the 1, 2 to the 2, 2 to the 3, 2 to the 4. It's 1024. So this is 1024 multiplications. So and what do you prefer? Lifetime of the universe versus 1024. 1024 is better for our web browser, right? So this is a great, great example for this is linear complexity. Linear in the exponent. The exponent is 2 to the 1024, and this is logarithmic complexity. So this is really great what Professor Parr showed us. Unfortunately, what is the problem with this really neat trick? Why can't we? Does this work with this E number there? Does this work? No, why not? What is the restriction on this great trick here? What do example 1, 2 and 3 have in common here? Was ist gemeinsam bei den 3 Beispielen hier? Ja. Exponent is even. It's more than even. It's Exponent is a power of 2. These are super special cases, right? This is 4 is in Zweierpotenz, is a power of 2. 8 is a Zweierpotenz, and 2 to the 1024 is a Zweierpotenz. In this case, I have a really fast algorithm. These are super rare, those numbers. I would like to have something for arbitrary numbers. And now the cool stuff parts. Now I'm going to show you a way of doing that. It's roughly as fast as this trick. It works for all the numbers. And it's really cool. And probably nobody of you knows that. This is not something we deal with in everyday life. And I love that algorithm. This is a square and multiply algorithm. I guess I shouldn't do that. So I start handing out these Bögen, evaluation sheets. Please do not start filling them. I promise I stop 5 minutes early today. Do it then. I just want to hand them out now, okay? Don't look at them. Take one, okay? This is the cool stuff, and it's bad timing what I'm doing here, right? So, coming back to the square and multiply algorithm. Other names for this method is the binary method, which is a name I don't think is that great, or left to right exponentiation, which is a name that I do like, but I prefer square and multiply. Okay? And again, this is the thing, please. Can you be quiet? Just watch. Es lohnt sich absolut. Nächsten 10 Minuten. Don't do that with a book. It's Sunday afternoon, 2 Stunden, if you do that yourself. Maybe 90 minutes, okay? But this is 5 minutes with me. Everybody's happy, okay? So we start with an example. And again, we saw for the special cases that the exponent is a power of 2, Zweierpotenz, it works. Now what happens if it's not a power of 2? And we start with an, I should do that here, okay. Example, I want to compute x to the 26, okay? And first I show you how it works, okay, without giving the algorithm, and then we look what are the rules behind that. Again, when you start with x, the first thing you can do, you can square. It's pretty much the only sensible thing to do. Then I multiply by x. I get x cubed, x to the third, x to the power 3, okay, x hoch 3. Now I multiply x by itself, I square, I get x to the 6. Now I multiply x, this result by itself again, because it turns into x to the 12th. I compute x times x to the 12th is x to the 13. And at the end, I square again. Somehow it works. It's not that bad, right? Again, remember the naive way, the stupid way, would have been x always multiplying by x, and it would be 25 iterations, okay? So here, I'm getting away with 1, 2, 3, 4, 5, 6 operations. And now let's look a little bit more detailed. What are the operations? I start here with the squaring. Right, this is squaring. Here is, I call this multiply, multiplying by x. Here I square. This is the squaring again. In this iteration, I multiplied by x, so I call this multiplying by x, I just call multiplication. And at the end, I square again. So if you ask me, please, Professor Parr, how can I compute x to the 26 quickly? My answer will be square, multiply, square, square, multiply, square, and voila, the result is correct, right? Are you with me? So what we need to know is what is the right sequence. I mean, if you replace this by squaring, you get the incorrect result. Everybody with me? So what we would like to know is what is the systematic way, when do I square and when do I multiply? This is what we would like to know, okay? This is why it's called the square and multiply algorithm and not the square and something, square and Fourier transform algorithm. It's only square and multiply. So it's a very simple idea is at the right moment in time I have to square, and at the right moment of time I have to multiply. And how do we do that? I could give you the pseudocode, you look at the pseudocode, you have no idea what's going on, okay? And I think there's a very nice way of explaining that, namely this rule, when to square and multiply, depends on something extremely simple, namely on the binary representation of the exponent, right? 26 is the important number here, right? So now we look at the binary expansion. This is 1, 1, 0, 1, 0 in binary, right? You believe me? This is 1, 2, 4, 8, 16, right? 16 plus 8 is 24, plus 2 is 26, right? This is a binary representation, okay? And now what I'm going to do with you now, and this is kind of the most important part of the lecture, not the second most important part of the lecture. I'm doing this stuff, and I'm looking at all the exponents in binary representation, and suddenly you see the light. I mean, does this seem arbitrary, zufällig, willkürlich? I hope so, say yes. So, no, if I look at the binary representation, you will see an extremely simple rule. There's a very simple rule, but you can only see the rule if you look at the bits, not if you look at the 26, okay? So let's look at the rule. So goal is to generate this bit pattern. We start with x, and x is really x to the 1, right? Is that clear? X ist gleich x hoch 1. So what we do here, we square, the result is in binary, right? This is x squared. Not that difficult. Okay. So what? Yeah, okay. Now let's first look at the next step. So the next step is I multiply x, which is x to the 1, by x to the 2. And now let's look here. It's Zwischenrechnung. What is binary addition by hand? Okay. 0 and 1 is 1. This is 1. Okay. So now I give you a little bit of pointer, and I think that's quite important to get kind of a visual feeling, visuelles Gefühl for this. What I'm going to tell you, these two ones that we generated, they're going to end up these two ones here, okay? And how, we'll just follow me, watch me. So the next thing is we square. Okay? Do you remember this rule here? Alpha to the what alpha to the a raised to the b power, this double exponentiation, what is that? A times b, right? Everybody with me? This is 9th grade, right? Not very complicated. So that means squaring is multiplying the exponent by 2, okay? This is not hard. So, but what happens if you have a binary representation, you multiply that by 2, what happens? Shift. It's the same if you have a decimal number, you multiply it by 10, right? 33 times 10 is 330, right? You shift it to the left, right? Yeah, to the left. So, okay. So, but what we mean by shifting to the left, what happens to the rightmost position, to the LSB? Becomes a 0, right? Okay. That means first very important step. Everybody awake here? multiplying is shifting the binary representation to the left, filling in a 0. Okay? Is that right? Is that right? Yeah. This 1, 1, if you square, is shifted to the left by 1 position, you get a 0. Okay? This is the first atomic operation, the first thing you can do. The first of only 2 things. This is 50%, halbe Miete. Okay? It's here. What would happen if we keep squaring this? Which bit pattern would we get? We would get 1, 1, 0, 0, 0, 0, 0, 0, right? Do we want that bit pattern? Maybe, not really, right? But what is good at this point is these 3 bits are these 3 bits we want to have here, right? So we are fine with these 3 bits. So what we can do at this point, we square again. What happens? Well, again, it's a shift to the left-hand side by 1 bit position. Okay, let's take a breath again. Are those 4 bits the bits we want to have here? Is this 4 bits here? No, right? What is missing? What would we like to have here? Was fehlt hier? Yeah. We need a 1 at this point, right? And how do we do that? Well, this is the other 50%. You multiply by x, and now again we have something that I showed here, which was easy. By multiplying with 1, you add a 1 at the LSB, it's the least significant bit position. And those 4 bits that you generated by now, almost graphically, fast graphisch, are those 4 bits here, okay? So what is the next thing we need? Well, we need another 0 here. What do we do? How do we get the 0 here? What is the next step? Square again. It's getting boring, right? And that's it. Okay, so we summarize. This is a square and multiply algorithm. That's our abbreviation, square and multiply, SAM, square and multiply algorithm. In words, so the first thing is scan. Scannen sagt Ihnen was, ne? Generation X. Ne? Scan, abfragen, abtasten, right? Scan the exponent bits left to right. That's what we did over there. You start on the left-hand side, okay, and you look at each exponent bits. Here are the rules. The rule is extremely simple. There are 2 things we do per exponent bit, right? Per exponent bit, there are 2 things we do. The first one is easy. In every iteration, jede Iteration, in every iteration, we square. And I use uppercase letters just to stress that. It means for every exponent bit, also jedes Bit im Exponenten, you definitely square. There's no question asked. You square, square, square. Okay, this is not conditional. You always square. For every bit that you have here, you square once. Okay? So, and this worked actually nicely in this case here, right? Square. So, but apparently, as we saw by the example, sometimes you have to multiply. And what is the rule for multiplication? Whoever can answer that is perfect learning experience today. What is the rule? When do I multiply? What? Yeah. Again, we're scanning the bits, right? Wir fragen die Bits ab. And there are only two possibilities, namely either a bit is 0, and then we don't do anything. It's easy. If it's 1, and only if it's 1, we also multiply by x, by the original value. Second, if current bit, also if das aktuelle Bit, if current bit is 1, Doppelpunkt, multiply by x. This is very graphic, blah, blah, blah. If you look in a more technical view is the pseudocode, which is actually on the book on page 182. So what you see in this box here, I call the exponent h here for whatever reason. For Hochzahl maybe, I don't know. I think I ran out of variables here. So we want to compute this here. This, what you see here, which I tried to highlight, this actual pseudocode, is this rule, the simple rule put into computer code. What I do here is t down to 0, and t, I don't know whether you can see that this t comes up here. T is the Bitlänge, okay? If t bits, you have to be a little bit careful. You ignore the highest bits, this bit ht. Das ist das MSB, das höchstwertige Bit. Highest value MSB bit is always 1 by convention, okay? So you start, in our case here, x to the 26. We really didn't start with the leftmost bit, but with the bit next to it. And the main rule is encoded here. 1.1 is we always square, and then here's an if statement. We check the current bit. If this is equal to 1, we also multiply by x. That's it. Very, very easy. Very, very easy rule. Okay. We don't have to talk about security. We did that before briefly. That's it for today. I would like you to fill the evaluation sheets and put them down here when you leave. Thank you very much.